So last time we basically started the in-depth study of sonar or ultrasonic sensors. And as usual, we started with the physics of it, right? So physics of acoustic waves is what we started studying. So at a very high level, we said that the principle of operation of all active sensors that we'll be studying, and specifically sonar, it's very simple principle. So basically, you have a transmitter or an emitter that sends out a signal. A signal goes into the environment, it hits the targets or different parts of the environment, and some echoes reflect back. And then the receiver part of the sensor collects those echoes, and then it needs to process them somehow and determine the range to each target as well as the bearing angle or direction of arrival to each target. And then as you do this process repeated for multiple targets, you can then basically reconstruct a 2D or 3D map of the scene by basically placing these points according to their range and their direction of arrival into a common frame of reference. Now, we started going in depth into the physics of it for sonar. So for sonar, basically, the signals are acoustic waves at ultrasound frequencies. And we first focused on the emitter or the transducer that sends the signals. So these are essentially like audio speakers, but they work at high frequency, so the signals are not audible to us, but they're sound waves, essentially. And we showed that the beam pattern of the wave that is generated by ultrasonic emitter, in the case, in general, it can be very well approximated, the angular dependency of it, by the Fourier transform of the shape of the emitter aperture, right? So in most cases, the aperture, as we'll see today, the apertures that are used are basically just plain circular disks. And in that case, you just take the 2D Fourier transform of a 2D basically disk or a circle, and it turns out to be basically this Bessel function that we showed. Graphically, it kind of shows is like this blue part of the picture here. Basically, your beam pattern, it has a main lobe where most of the energy is focused, and then you get a number of smaller side lobes around it. And the main lobe, basically, it has some beam angle that is 2 times theta 0, so it goes from minus theta 0 to theta 0. And theta 0 is given by this expression here, which is the sine inverse of some constant, 0.61, times velocity or speed of sound in that medium, divided by A times F, where F is the frequency of the ultrasonic wave that you're generating. Basically, it's the frequency at which the emitter is vibrating, and A is the radius of that disk that is your transmitter or the emitter. So it is desirable in most cases. It's a little application dependent, as we'll see. But in most cases, if you want a good angular resolution, you want to basically focus your beam as tightly as possible. So you want their theta 0 to be small, which means according to this expression, the denominator here should be large, which means either you go to higher frequencies or you use larger apertures to basically focus your beam better. Then, of course, we are interested in the echo, not just what we transmit, because we need to process the echo to do sensing with it. And so we continued along those lines. We said, okay, you send a ultrasonic wave according to this radiation pattern or beam pattern. It hits a target. If you assume your target is small, this is just an assumption for us to be able to simplify the math, the return echo, when the target is pretty small, you can very well approximate it with spherical waves, okay? So you hit it with kind of like a focused beam, but what echoes back to you, you can estimate it as spherical waves. And the spherical waves, as we showed, basically their amplitude drops by 1 over distance, right? So on the return path, the echo that's coming back towards the sensor, there's going to be, if that range is rho, on the return path, there's going to be a 1 over rho attenuation, basically, just according to the physics of the spherical waves. And then we said that if most of these components, they can operate both as a transmitter and a receiver. So if you have one of those transducers, then for collecting back the echo, the sensitivity of that is going to have the exact same pattern, angular pattern, as the transmit, because it's the same physics, basically. So then you get the same, basically, Bessel function as your sensitivity. Maybe I should go to this slide here, because we can also look at the expressions together. Okay, so then basically the sensitivity of your receiver, S of theta, is going to be the exact same pattern as its beam pattern that it's radiating or emitting, the same Bessel function dependence. And but also there's a gain factor, and the gain factor basically is a measure of how much of the return echo's energy your receiver is collecting, and that is proportional to its area. The larger it is, more of the acoustic energy is captured by it, right? It's directly proportional to the area. So that gain factor of the receiver is some constant. I'm calling it zeta times a squared. So a squared is kind of like a measure. If it's a circle, basically, of radius a, then pi a squared is the area. So I'm just lumping in the pi into that constant. So some constant times a squared is a measure of the gain of your receiver. So then what is the received echo at the end of the day? So the echo is a multiplication of a bunch of factors. It, of course, depends on the range and angle, right? Those are the two factors. So this term here, P of rho and theta, is your transmitted beam pattern, right? Then it hits a target, and the target would also have some acoustic reflectivity, right? It does not echo back 100% of the energy that hits it. You know, some materials absorb some of the vibrations, for instance, right? So there's this delta factor. That's a number between 0 and 1, which is the acoustic reflectivity of the target that we're hitting with the acoustic wave. Then you get the 1 over rho, which is the attenuation according to the spherical wave propagating back to the sensor. Then you multiply by S of theta, which is the sensitivity, the directional sensitivity of your receiver. And finally, you multiply by the gain factor G, right? And that is the full equation that gives you what is the dependency of the echo that you collect back. What's the dependency on range and direction of arrival? So how does it depend on rho? How does it depend on theta? And as you see here, the dependency on rho turns out to be a 1 over rho squared. Okay, so by square of the distance to the target, we basically lose signal. And the dependency on the angle of arrival, or the bearing of the target, is the square of this, basically, Bessel function. Okay. Now, this is extremely useful equation because first it's easy to evaluate, right? We can plug in numbers into it, like everything should be known, right? If you're analyzing a case, you say, oh, I'm designing a sensor, I want to see if I can detect a target that is at 20 meters at a 30-degree bearing angle with a reflectivity or acoustic reflectivity of 50%. And then I have an emitter which has an aperture radius of an inch, let's say, and my frequency is 40 kilohertz. Okay, you plug in everything, and then that directly gives you what is the echo amplitude that you collect back. And then that kind of it's a very easy way of determining, okay, am I going to get enough signal to be able to, you know, detect it successfully, or is it compared, for instance, to the noise level of the electronics I'm working with? Is it going to be below noise floor? Is it going to be above noise floor? So this kind of gives you a first order, a very easy, first order check of what you can detect and what you're going to miss as a function of range and bearing angle and the reflectivity of the targets. So it's very, very useful, but also it's extremely important to, as you do these types of analysis, remember all the assumptions that went into this, right? So this equation, there's a whole bunch of assumptions. As we were doing the derivation, we made a bunch of assumptions, and if one or some of those are not valid for the case that you are analyzing, then your results might not match what you get in reality. So very specifically, for instance, what were the assumptions that went into this formula? We assumed a circular emitter, right? If your emitter is not circular, well, you're going to get a different beam pattern. What else did we assume? We assumed a perfectly, harmonic sinusoidal waveform. If your waveform is some broadband waveform with other frequency components in it, then your radiation pattern is going to change. We assumed we are operating in the far field. So if you're doing near field sensing, well, some of these assumptions break down. So it's really, really important. And that's why instead of like in one shot showing you this expression and saying that's the echo amplitude of an ultrasonic sensor, I really walked you through all the steps from the very basic physics to here, so you see what assumptions were made. And for your specific studies, if one of those assumptions is not valid, that's fine. You can go back and go to the point where we made that assumption, remove it, and continue the derivation without making that assumption. So very specifically, for instance, if your aperture shape is not a circle, that's fine. You go take the Fourier transform of whatever the shape of your aperture is and use that formula instead of the Bessel function that we have here. Okay? So that's really, really important. And it's really when, like this formula here in 90, 95, maybe 99% of, typical cases, it just works fine. And most people just use it, and they don't even, bother or know about the assumptions that go into it. But it's really that 1% of the cases where things don't work, and then somebody needs to figure out why it didn't work. That requires the in-depth knowledge of, all the physics and the assumptions that went into it. And that's exactly that 1% is what differentiates really, really top engineers with others. And that's why we bother with the physics here. Okay, any questions? All right, let's continue. So now we know the physics. So let's talk a little bit about these transducers, the emitters and receivers that are used. There's different technologies that are used to built these transducers. Specifically, there's three main types that are used for sensing. One is called electrostatic. So these ones are pretty high bandwidth, and they have good sensitivity. They require very high voltages to derive. So you might need like 100 volts or multiple hundreds of volts to derive them at acoustic frequencies. And they cannot go to super high frequencies. So you're typically limited by about like 150 to 200 kilohertz in terms of operational frequency, which is fine for robotic sensing. But for instance, they're not useful for medical ultrasound because they don't go high enough in frequency. Then you have your piezoelectric transducers. So these operate based on the piezoelectric effect. And they have low bandwidth because piezoelectric ceramics are typically resonant. So they only resonate at a very sharp frequency band, so that you can't do broadband sensing with these. But they don't require as high a bias voltage as the electrostatic, and they can go very high in operational frequency, up to a few megahertz. And finally, you have your MEMS transducers. These have very high bandwidth, very good sensitivity, and they can operate at extremely high frequencies. You can go up to tens of megahertz with them. Super compact, and they have all the benefits of the MEMS processing, like you can co-package your electronics with a transducer in one chip and so on and so forth. The drawback is in MEMS, you cannot make very big apertures. So you are, because of the process limitations, you're limited to small apertures, which, as we know, would then limit basically your beam width. So with MEMS, you're going to get very small a, which means very large, theta 0. And then the trick people play to basically counter that is in MEMS, you can, instead of one emitting aperture, you can generate an array of them, so a bunch of them very closely packed together, and then effectively together they can act as a larger aperture for you. Let's look at, and all three types, by the way, they can operate as both transmitters and receivers. So these are bidirectional, can be in principle bidirectional transducers for you. There's no limitation on that side. So let's look at some pictures so you get a better idea of what these look like. So here's an electrostatic transducer, extremely simple construction. So there's basically a ring. And then inside there, the ring is just for structural purposes, so you can mount basically different pieces to it. But the key piece is there's a grooved metallic plate, and then there is a very thin foil on top of it. And the way this device operates, and here you get an idea of the size, you know, compared to a quarter there. So these things are like an inch or two in diameter. And then if you look at the cross section of the groove and the thin foil on top of it, so you get basically these peaks and valleys inside on top of the groove plate. And then the high voltage is applied between that metallic foil and the metallic groove plate. So you get your electrostatic force between the two, and the force can basically pull the metallic foil into the grooves. So when it goes into the grooves, it makes this shape, and then as you oscillate the voltage, you basically vibrate the thin foil on top of the groove plate, and it generates these circular basically waves on top of it, which then emit ultrasonic waves. And just to protect the foil, because it's very thin, usually you put like a housing or a grill on top of it, so you can't, you know, touch it or puncture it. So that's your electrostatic transducer. And then here's one example of a piezoelectric, also super simple construction. So basically, this is a device. In terms of the size, it's comparable to the electrostatic. It takes up a little more volume. The electrostatic is more flat, but in terms of the diameter, it's very similar. And then if you look at the cross section of this, basically these two darker elements here, those are the piezo ceramics. And the way it's constructed, basically you sandwich your piezo ceramics between two pieces of mass, and you put them in tension with some compression bolt, right? So there's some tension applied or compression applied to the piezo ceramics, and then as you apply a voltage to the electrodes, the voltage is applied to the piezo ceramics, and then they start through the piezoelectric effect, they start vibrating at their resonance frequency, and then that vibration is coupled to the mass. So the mass vibrates, and then you can then bond the mass to some output phase, which becomes basically your emitter aperture, right? And here's an actual cross section of a device. So you have your piezos here, and then that's the compression bolt. You have the two masses, and at the end of the day, this top plate is what your final aperture of the emitter or the receiver is going to be. Okay, so that's piezo. And finally, there's the MEMS. And here, again, you get a sense of the scale. You see how much smaller MEMS is compared to the other two. I mean, it's really, really tiny. And the aperture hole on this particular device is just a half a millimeter. And there is a lot actually packed into this tiny package that's just a few millimeters by a few millimeters. So if you open it up, so the way it's constructed, it's actually like a double-decker design. So on the top, you have your MEMS device with the emitter. And at the bottom, you have all the electronics. So you have, you know, your waveform generator, your amplifiers, your ADCs, your signal processing. So this basically, you can co-package everything into a small chip, and this thing is the full sensor then, not just a transducer. You can have everything in a tiny package. And then if you zoom in and look into your aperture hole under a microscope, you see this tiny MEMS membrane. And then if you zoom in a little more into that, this tiny little circle, that is your emitter aperture, which is, you know, sub-millimeter in dimensions. And it's suspended with these super thin, bridges. And then the principle of operation is exactly like your electrostatic transducer. So basically, this is your thin membrane. And then a voltage is applied, an alternating voltage between the membrane and a fixed metallic surface. So again, you get your electrostatic alternating force, which causes vibrations of the membrane up and down. And then that's how you generate your acoustic wave. But again, the point here is you have to notice how small that aperture is. You can make an array of them, as I said, but if you just use one, like in this device, you get a tiny, tiny aperture, which means this device would generate a very broad beam for you, which for some applications might be actually desirable. It's not necessarily a bad thing. So for instance, if you just want a proximity sensor for a vehicle parking assist sensor, you typically want them to have very broad beam patterns so that no matter where the target is, you can detect its proximity. The price you pay is then you lose sensitivity in bearing, right? Your bearing angle estimation might not be as accurate. Any questions? Yes?
I'm a bit curious, like, in terms of MEMS, the amplitude of the signal is put use. It feels this is going to be smaller than the ultrasonic, so piezo and electrostatic sensor. Is that true?
The amplitude of the actual acoustic wave, you mean? Yes, and that's also because you have just a tiny surface that is vibrating. So you just generate less energy, basically, acoustic energy, and energy is proportional to the amplitude or the square of the amplitude. So yes, you do get less, which means also your range would be more limited because you're not sending as much energy out. That's exactly right. Okay, so now we understand the physics of acoustic waves. We also looked at how these transducers are made in using different technologies. I think we are ready to start looking at the system architecture to understand at the system level how an ultrasonic sensor works. The system block diagram is extremely simple, actually. So basically, on the transmit side, you have some local oscillator that generates, the base frequency for your acoustic wave that you want to send. Then you have a waveform generator. We'll talk more about this, but you typically don't just send, a pure harmonic. You send some sort of a pulse shape. Then you want to amplify that, and that's your amplifier in electronics. And as we said, some of these transducers, like the electrostatic ones, they require very high voltages, like 100 volts or more. In those cases, you also have a high voltage transformer in the path, so that's just to get you to the very high voltages you need, because you can't directly generate those in electronics and CMOS or something like that. You basically get help with the transformer effect. You couple that basically amplified waveform to your transducer. Here we are showing one where the same component is both the transmitter and the receiver. So you first transmit your wave, and then you also collect the echoes. And the echoes come to the receiver path, basically. On the receiver side, also very simple. You just amplify it. As we do in any sensor, usually the first thing you want to do is to amplify because you want to maximize your signal-to-noise ratio. Then you apply some filtering to get rid of out-of-band noise and just keep, the frequency content where there is signal. And then you digitize it through an ADC, and then you do some processing in DSP to estimate your range and bearing angle. And we'll talk about the processing. Now note that this is kind of like a generic block diagram. Specific systems might be different from this in certain aspects. So some of them, for instance, might not have the high voltage transformer because, for instance, if you have a MEMS device, it doesn't need high voltages to operate. So then you don't put the high voltage transformer in them. Or sometimes you might have a separate transmitter and a receiver, as we'll see in some cases. You separate out your transducers, use one only for transmit, use the other only for receive. But at a high level, basically this block diagram captures the essential functions that need to happen inside a sonar system. So here's an example. I think we've all seen these ultrasonic sensors in the bumpers of the cars that are used for parking assist. So these are the tiny, circular indentations that you see. There's usually 4 of them on each bumper. So those are ultrasonic sensors. And if you take one of them out and look inside it, now we fully understand at a system level what's what. So typically those have a piezoelectric transducer, which is connected to some PCB here. And then on the PCB, you have a transformer to generate the high voltages. And then you have a silicon chip with all the electronics. And the electronics basically is everything we showed in the block diagram. There's the oscillator, there's the waveform generator, and then on the amplifiers on the transmit and the receive side, filter, ADC, and possibly some DSP on board to basically process the signals. Some of them you don't do the DSP on board and just give you, digitized signals, and then you can have a separate microcontroller or some compute elsewhere that does the processing for you. So that's what these look like, and there's several companies that make them. This one is from Bosch, for instance. Okay, so yes?
So on the previous slide, you said some systems do simple ranging in the analog domain.
Correct, yes.
Can you talk a little bit more about that?
Yes, and thanks for pointing that out, because I think I skipped over it. But we are talking about this point, right? It's do simple ranging in analog domain. So in some cases, if you're not interested in doing full mapping, and for instance, I think one example is like the parking assist sensors, where you only want to detect proximity, okay? You don't need to go to the trouble of, digitizing your signal and then, doing fancy DSP on a microcontroller or something like that. What you can do is, in analog, build very simple circuitry that just do some thresholding on the received signal, and if it goes above a threshold, they kind of say, oh, I'm detecting something, and this is the range. We'll talk a little more about it in a few minutes, but basically, those sensors are not usually extremely useful for robotics, except, again, if you are interested in just a very simple proximity detector. But if you want to do, proper mapping with bearing angle detection and things like that, you have to digitize your signal and do some DSP. Okay. So one thing we haven't talked about yet is, if I go back here, so there's this waveform generator here. But what are these waveforms that are used for sonar sensing? So there's 2 main categories of waveforms that are used in sonar. First category is short pulses. So some sonar systems basically generate finite duration short pulses, so they're somewhere between tens to hundreds of microseconds, and they send these pulses. So your transmitter basically sends a pulse, and then it's silent until all the echoes are received from that pulse, and then it sends another one. So it's periodically sending pulses, but the pulses are short. So there is a finite duration that you transmit, then you're mostly silent, okay? And then you send another pulse, and then you send another pulse. So the waveforms are repetitive series of finite duration pulses. The hardware and algorithms that are needed to generate the pulses and also process the echoes to do ranging and bearing estimation are very simple. And this type of sonar is called pulse echo sonar, by the way. But it also comes with some drawbacks. So typically these systems are not very robust to noise and interference, and also they're limited in how many measurements you can do per second, because most of the time you're not transmitting anything. You just send a pulse, you're listening for all the echoes, and then you send another one. So that sort of, as we'll see, limits how many measurements you can do per second. Then the second category of waveforms that are used, those are continuous waveforms. So your transmitter is continuously, never stops. It's continuously transmitting waveforms. Specifically in sonar, these are called continuous transmission frequency modulated sonar, or CTFM sonar, excuse me. Also called frequency modulated continuous wave, or FMCW sonar. FMCW might be familiar to you from radar, basically community, because that's what these systems are called in radar. But CTFM and FMCW, exact same principle. Basically, the system is continuously transmitting some frequency modulated signals, and we'll see exactly what the frequency modulation is today. There's certain benefits to this. They typically need less bandwidth. The average power that they send is lower because you're spreading out your transmission over longer durations, so you don't need to send very high peak powers. So there's less, nonlinearities and things like that in the system. You can do a higher number of measurements per second, as we'll see again, because you're continuously transmitting your signal. You're not limited to short pulses. You will be more robust to noise and interference in these systems. But this also comes with a bunch of trade-offs. So you need more complex hardware, you would need more complex DSP, and certain types of movements in the target or platform might cause issues for these systems, as we'll see. So there's always trade-offs, right? It's not like pulse echo is always better, is superior always to CTFM, or CTFM is superior to pulse echo. The thing is that for pulse echo systems, and here we are talking in the context of sonar, but exact same thing, as we'll see, type of waveforms are used in radar and LiDAR as well. What really is the main drawback is the fact that the type of DSP, signal processing, that you can do is very limited in these systems. Because of that, they don't improve much over time, because as over time you're coming up with better algorithms, more interesting ways of doing detections or denoising or filtering and things like that, and most of those are not applicable to pulse echo systems. But in CW systems, there's a lot more you can do in DSP, and because of that, these systems are in terms of the performance, are getting better and better and better over time. So there is a shift in the performance, and I think eventually we might get to a point where, except for cases where you want to build something which is very low cost, or you need very simple hardware, you might be kind of completely ruling out eventually. That's not where we are today, but eventually we might completely phase out pulse echo systems for more advanced robotic applications. Okay, so now we're going to study these types of waveforms in detail, and also the type of signal processing associated with each of them. Starting with pulse echo ranging. So how do you do ranging? Later we'll talk about bearing or DOA estimation. Right now we're just talking about how do you estimate the range to the target. So in pulse echo systems, there's two types of pulses that are used. First type or category of pulses, they're called narrowband pulses, and those are very easy to generate. They don't take a lot of frequency bandwidth, and they're typically more robust to noise, again because they're very low bandwidth, so you can filter out your received signal just at around the bandwidth of the pulse and reject a lot of noise. And then we have wideband pulses. So those, again, there's always trade-offs, right? There's no free lunch ever when it comes to these types of sensing applications. So with wideband pulses, you can get better ranging resolution. Also, you can do some very interesting stuff. So, for instance, because you have a lot of frequency content in the return echo with the wideband pulses, you can use that spectral information to do some types of classification. So, just by looking, for instance, at the FFT of the return echo, you can classify different types of objects, like a human versus a car versus something else. And this idea, for those of you who are familiar, for instance, with the microdoppler effect in radar, this is kind of along those lines, but done in sonar. And also with wideband, you can get lower side lobes in the beam pattern. Okay, so what are the drawbacks? Again, there's going to be more complexity to the hardware and more complexity to parts of the signal processing if you want to do fancy stuff like this. Let's look at some of these pulses so we get an idea of what they look like. So there's these plots. The first two, starting from the left, are narrowband pulses. So the narrowband pulses, let's look at this middle one first. Basically what it is, it's just a pure sine wave, right, at a fixed frequency, 49.9 kilohertz, with a rectangular window applied to it. So the rectangular window basically determines your pulse duration. And then within that duration, you're just sending a pure sine wave. And that's why it's a narrowband signal, because there's just most of the frequency is going to be, the energy is going to be at that 49.9 kilohertz frequency. The left one is basically the same idea. It's a slightly lower frequency at 40 kilohertz. It's just that the window applied to it, or the pulse shape, is more smooth. Instead of like this sharp rectangular one, it's a smoother, basically, pulse shape applied to it. So those two are the two examples of narrowband. Again, there's tons and tons of like different pulse shapes that you can do. You can come up with your own, and there's always, you know, some trade-off in performance according to, you know, the parameters of the pulse. So it's not like these three, this is it. You can always come up with new ones, and there's many of these. And this third one is a wideband pulse, and as you see, it's basically just, well, there's a bit of transient, but it's basically just this one pulse, short pulse that you're sending, and that pulse is just 10 microseconds. So it's kind of almost, not exactly, but close to like what a delta function would be. It's very, you know, very narrow in time, which means in frequency it's going to be broadband or wideband. Okay? So, and then this is just one pulse. So again, remember the way the pulse echo sonar works is it periodically sends these, right? So if you look at like your time axis, what the TX is doing, that's bad. Let's clean it up. What the TX is doing. Let's do like if it's a wideband case, so it's going to send one of those pulses, then it's silent, then it will send another one and another one. And when it's silent, that's where the receiver is collecting echoes. And when all the echoes are basically back, then you send another one. So there's some periodicity to the transmit. But most of the time, you're not transmitting anything. That's how pulse echo works. Okay, so how do we do ranging with these pulses? Let's talk about that. So this principle that I just told you, you transmit a pulse, and then you just wait for all the echoes to come back, and then you transmit another one. So this is called, it's basically like a TDM, or time division multiplexing principle. So you're kind of multiplexing the time between your transmit and then your silent. You're just, you know, hearing back the echoes. And how do you decide the periodicity of like when to send the pulses? It's typically fixed, not adaptive. And the way that's calculated is that you decide on a maximum detectable range, call that rho max, okay? And that you can calculate based on the physics, like that expression we looked at, which gives you the echo amplitude. You can plug in some numbers into it, and find, okay, I think that's the maximum range, 10 meters, 15 meters, something that I can detect based on the amplitude that's coming back and what you think your receiver can successfully process. So if that's your rho max, the round trip delay for that range, so your tau max basically is equal to what? It's 2 times rho max divided by the speed of sound divided by v, right? So that's the maximum round trip delay time that you have. And this is how much you want to wait after sending each pulse. So the pulses that you send, you want to wait a tau max between them to make sure all the echoes are back. Or if you invert that, like how many measurements you would do per second, that's 1 over tau, right? Which is v over 2 rho max. That's the rate of measurement that your pulse echo system would do. And then in terms of, again, how do you find your range, that's just the time of flight principle. So what the receiver needs to calculate to do ranging is this tau, or time of flight delay, and then you do speed of sound times that divided by 2. Remember, why do you divide by 2? Because tau is the round trip delay. So you divide by 2 to make it your one-way delay, and then multiply by the speed of sound. Yes?
So it sounds like you arbitrarily decide on the rho max beforehand, but isn't it possible that your sound can reflect on a surface that's further than rho, and then it'll be processed in the next set of echoes?
Yes. So I'm just going to repeat the question. So the question was, okay, so we're going to decide on some rho max based on some calculation, or you do some sort of analysis based on the physics, and you say, okay, I think that's the maximum range that the system can detect. But there is always a risk, as you said, that you can have a very strong acoustic reflector at a distance longer than rho max, okay? And that would echo a signal back that you still detect, and it's strong enough, but that kind of messes up your calculation, because you assumed, now you're associating that echo with the pulse that was sent after the original pulse, right? So your tau calculation is going to be completely wrong. And that's exactly true. It does happen, and that's why you're never perfect, right? Some of your range measurements are completely wrong, and this is one of the effects that can introduce that kind of error. You always can have a very strong reflector. It's not the biggest factor, as we'll see. There are things that are much, much worse than this. But every now and then, yes, you can get something that is at a range higher than the max range you assumed when you were designing your system and algorithms, and that could give you a false positive detection, basically. Okay, so how do we do ranging? So we need to estimate time of flight, right? And there are two main type of algorithms that are used in pulse echo sonar when it comes to the time of flight estimation. One is called threshold-based ranging, which is the simplest thing one can do. We'll talk about it. And then you can borrow an idea from GPS. And when we were studying GPS, there also you had to estimate time of flight, right? And for GPS, we use this idea of matched filtering or correlation to do time of flight. Here, it's the same thing. If you want to measure time of flight, one of the things you can do, if you transmit signals with good autocorrelation properties at the receive side, you can correlate them with a replica of what you sent, and then the correlation peak would be proportional to the time of flight. So that's also another idea that we'll talk about. But let's talk about the simple one, the threshold-based ranging. Extremely, extremely simple idea. So basically what you do is, here's your P echo, so the received echo, either in continuous time or after the ADC. So that's why you have the T or an N version. The N is the index after ADC sampling. And so your echo is a function of the range rho and the bearing angle, or DOA, of the target. What you do in threshold-based ranging, first you rectify it, but basically take like the absolute value of it. Then you integrate that rectified waveform, and you monitor the output of your integrator as it's doing the integration. As soon as it crosses a set threshold, you say that's my detection, and you check the time at which your integrator output crosses the threshold, and you declare that as your round-trip time of flight. So graphically, here's what's happening. So you have your echo waveform coming back. It hits the receiver at time tau. So this tau is the ground truth time of flight that you want to estimate, right? That's the actual physical time of flight. That's when you start receiving the echo, right? Then you rectify this, so this is the absolute value of your waveform, the rectified version, and then you pass this rectified waveform to an integrator. So what happens is that, well, there's nothing out of the integrator until you get some signal, and then you kind of start integrating, and at some point, the output of your integrator crosses a threshold, and then at that point, you check what time it is, that's tau hat, and that's your estimate of the time of, or the round-trip time of flight. So right off the bat, you see that it is a very simple algorithm, but it has a big problem, which is your tau hat is never going to be the same as tau. There's always going to take a little bit of time for the integrator to cross the threshold. So it is always a biased estimator, right? That's very important to note. You never get a perfect estimation out of this, and it's always biased. What makes matters a little worse with this detector is that not only your estimate is always biased, but also this error in your estimation, and the error is the delta tau, which is tau hat minus the ground truth tau, is also a function of the strength of the echo that you receive. So if you have a weaker target, either a weaker reflectivity target or a target that is at a further distance, because we know echo amplitude is also proportional to 1 over range squared. So you get a smaller amplitude echo for further away targets. So if you have another target with a smaller, I'm just going to overlay it in green, with a smaller echo amplitude, and you pass it through the same integrator, it's going to do the same thing, but it's going to pass, because it's a weaker signal, it's going to pass the threshold at a much later time. So this is going to be the tau hat 2 of the green signal. So your basically error in estimation is going to get worse and worse, either when for further away targets or the targets that are less reflective. So it's not a great estimator. So if you want, applications, I'll be with you in a second, applications which need, precise ranging, you shouldn't use the threshold base. Yes?
For this type of application, how would you go about sensing like 2 different targets?
That's also a great question. So the question is, what if you have echoes from more than one target, right? So 2 cases can happen if you have more than one target. Either they are at the same range but at different angles, okay, which means basically, at the same time that you have this PE, there's a second target whose echo is hitting the receiver at the exact same time. And with that, there's no way you can distinguish them, right? Because you get the sum of the 2, and then you cannot tell. You just detect it as one target. The second case is if the targets are at different ranges. So if they're at different ranges, the echoes are going to get to you at different times. So you receive the first target, and then a bit of time goes by, and then you receive another echo. This you can detect, but what you would need to do, and that's actually what good receivers do, is that at the output of this integrator, as soon as it crosses a threshold, which we call a target detection, they reset the integrator. So it crosses the threshold, they reset it, go back to 0, and then integrate again. So if another echo comes, you can detect it. Okay, so you see right off the bat, this comes with very serious limitations, but it's actually even worse than that, as we'll see. So always biased, and also your time of flight estimate depends on the echo amplitude. So echo amplitude is, as we know by the analysis that we did last time, it depends on a bunch of factors. One is the basically acoustic reflectivity of the target, how much of the energy echoes back. Then there's range, because there's a 1 over rho squared dependency on the echo amplitude. The third one is angle dependency, right? That Bessel function dependency, for instance, determines also the reflectivity or the echo amplitude, not the reflectivity, the echo amplitude of the target. So targets that are at larger bearing angles, we get much weaker signals from them. And with this type of detection, weaker signal means bigger error in your ranging estimate. So let's study that. I think it's important to understand that how serious, especially that bearing angle dependency of the ranging error is for this type of detector. So to do that, we need a signal model. Kind of like our physics accurate signal model is this expression that we derived for the echo amplitude. I'm going to factor out the range dependency. So let's say we're looking at targets at a fixed range rho, Okay, we also fix our frequency and other parameters. We're just going to look as a function of theta, which is the bearing angle to the target. If you just hold your target at a fixed range and just change the angle, how is the error in our ranging going to change as a function of theta? So the theta dependency of the echo amplitude is this square of the Bessel function that we derived. This is a pretty accurate signal model, but it's difficult to work with. We don't want to work with Bessel functions when it comes to this type of analysis. So again, remember, everything else is lumped into this P0. So P0 has your aperture, geometry, frequency, the rho squared, all of that. But you're fixing all of those, just focusing on varying theta, which is the DOA angle. So to get something that is easier to work with, it turns out that, so this Bessel function squared thingy, remember, as a function of theta, it has a main lobe, and then it has a bunch of smaller side lobes, right? And the main lobe, if this is theta equals to 0, it's between plus theta 0 and minus theta 0, right? Now, it turns out that the main lobe of this can be very well approximated by a Gaussian function. So basically, for thetas that are in the main lobe, less than theta 0, you can approximate your echo amplitude by the P0 times a Gaussian function, which is minus theta squared over 2 sigma squared. What is sigma? Sigma is just the variance of the Gaussian, and it's chosen such that the width of the Gaussian matches the width of your echo amplitude, basically. So graphically, this is what it looks like. So this is for a real transducer that I did this. The transducer had a aperture radius of 1.8 centimeters. It was operating at a frequency of 50 kilohertz. So those numbers you plug into the Bessel function and you plot it, and the blue curve is the actual, angular dependency of your echo amplitude. And then the red is a Gaussian that I fit to it. And as you see, for thetas that are between, say, plus and minus 10 degrees, the red and the blue are almost on top of each other. So we can use the Gaussian function as our signal model to analyze our ranging error. It's much, much easier to work with. Okay? So let's see then how the error in ranging for the simple threshold-based detector varies as a function of the angle of arrival or the bearing angle. So the way we do that, we need to basically, the detection criteria, remember, is the output of our integrator crossing a threshold. Right? So let's look at that. If this, we call I of theta and t the output of the integrator, which is basically the integral from 0 to t of the absolute value of the echo amplitude, or the rectified echo amplitude, right? Now, we're going to make one more simplification here, again, just to get a signal model we can analytically play with. Remember, if I sketch it here, the rectified echo amplitude, if it looked something like this, right, for like one of those narrowband pulses that we were working with. We are going to approximate that by just a rectangular pulse of constant amplitude. Okay? Why? Because then the integral we can do analytically and look at the results easily. So what happens is that, so the amplitude, we call that just P echo of theta, right? We take that out of the integral, and then the integral, so it starts at time tau, which is the time of arrival, actually, of the pulse, and we're integrating over t, right? So then you integrate from tau to t of just t. So then the result is basically this. What we have plugged in, well, P0 is just that constant that lumps in range and geometry and frequency and all that. We have our Gaussian approximation to PE of theta. Okay, so that's e to the minus theta squared over 2 sigma squared. And this t minus tau is basically the integral, right? So this now we have an analytical formula for the output of our integrator. And then remember, as soon as this I crosses a threshold, that's where we declare a detection. So when your I of t and some tau hat equals the threshold that we call big T, that is the time of arrival, basically, for us. So then we just use this expression here for I, and we solve for our estimate tau hat of the round trip delay, and this is what you get. So your tau hat is the true ground truth tau plus this error term. That's your estimation error. And as you see, it depends on a bunch of things, right? It, of course, depends on your threshold, right? And it seems like, okay, this tells me if I want a low estimation error, I should choose a threshold as low enough. Why not even set it to 0, right? Why not? Set it to 0, error term goes away, everybody happy, right? Tau hat equals tau. Why not do that? Well, because there's always noise, right? So the output of your integrator is always greater than 0. Because even when you haven't received any echo, there's, noises and a little bit of interferences and other effects. So, I mean, the picture we're looking at here, everything, looks nice and ideal. But you can never have a 0 threshold, because if you set your threshold too low, any bit of noise spike or something that is randomly generated in the system causes that output to go to 0. So you're going to get a ton of false positives, basically, if you set your detection threshold to 0. So bad idea. We don't want to mess with T too much. You usually even set it a bit conservatively to limit your false positives. What else? P0 we want large, right? And P0 is basically a measure of like the amount of echo you get back from the target. So stronger targets are good, right? Those give you big P0s. Closer targets are good, right? Those give you big P0. But it's not really a design parameter, right? It is what it is according to the distance and the acoustic reflectivity of the target. And then you have this really, really, really concerning term here. And as you see, your error is exponential in theta squared. So as you make your angle of arrival larger and larger, this error term can really, really blow up. And that's actually what happens when you do that. If you want to, instead of like thinking in terms of the tau, if you want to actually think in terms of the range error that you make in meters, for instance, we can convert that to range with a simple, our time of flight conversion. So delta rho is the error that you make in ranging, and that would be speed of sound times delta tau, right? Your estimate of the round trip time of flight minus the actual time of flight times 2, and then we plug in our expression for tau hat. This is what we get. So the range error in meters is given by this expression. The theta dependency is the same, right? So it depends on the e to the theta squared over 2 sigma squared. So if we plot this, we'll see it can be really, really a big issue in certain cases. So what we're plotting here, we are looking at the ranging error, right? The error in the range estimate as a function of the bearing angle of a target. We're looking at 2 different targets. One is a target of very high acoustic reflectivity, like a wall. The other one is a target with very low acoustic reflectivity, like a thin pole, for instance. And both are at the same range. So we're fixing rho at 1.5 meters, and we're just changing the angle of the targets. Right? So the difference is one of the targets has a very large P0, and that's the wall, for instance, and one of them has a very small P0, which is the pole. That's the reflectivity of the target. And then we look at the error as a function of theta, and if you look at the one for the pole, even for a 10-degree angle of arrival, you can be a meter off in your range estimate. For 12 degree, I mean, this thing blows exponentially, right? So 15 degrees, it can be many, many meters. So that can be a big, big issue. For targets that have a high reflectivity is not as bad, right? And again, why is it not as bad? Because this 1 over P0 term in the error term. So if your P0 is large, that really limits your ranging error. And that's why for a wall, it can be at 15 degrees, and you still estimate the range pretty much correctly. And it's really like beyond 20 degrees or beyond 15 degrees that your errors for a very strong target start to blow up as a function of angle. So again, we did all this analysis, and just to show you the simple threshold-based ranging works, but it has very significant drawbacks. So if you're working on an application where you need accurate ranging, accurate mapping, you don't want to do this probably. This is not the best algorithm to work with. Any questions? All right, so the second type of algorithm you could use for a pulse echo sonar is doing matched filter ranging. So let's just remind ourselves, when we were talking about the GPS, we did this very general derivation, if you remember, that we said, if you have some transmitter that is transmitting some signal x of t, and then you have a receiver that receives some attenuated and delayed version of x of t, like alpha times x of t minus tau, and you want to estimate tau, and if you set your basically criteria as minimizing the mean squared error in your estimation of tau, then the optimal detector is what we call a matched filter. And what a matched filter does is that it takes the correlation of your received waveform with a copy of the transmitted waveform. You evaluate the correlation, you find the peak, and where that peak happens is your minimum mean squared error estimate of the time of flight delay, right? Exact same thing you can do for sonar, except now your transmitter and receiver are co-located, and your tau is the round-trip delay instead of the one-way delay between the transmitter and the receiver, right? But the exact same thing. So you receive some echo waveform, right? And because you transmitted it yourself, you know what waveform it is, so you can also generate a local replica of it, correlate the two, right? And then find the peak in your correlation, which is the argmax of the correlation squared, or the absolute value of the correlation, and then that gives you your round-trip time of flight estimate. Exact same, again, math and principle as what we did in GPS, so I'm not going to spend too much time on it. Again, F sub S is your ADC sampling rate, and N hat tau is the discretized index corresponding to your actual time of flight. So it's the floor of tau over T sub S, where T sub S is the sampling interval. And again, we all know that the correlation is given by this basically linear filter here. Here, I think I'm dropping a constant factor here, like that 1 over k thing. I've just dropped it because it doesn't matter. You're just looking for a peak, right? You don't need to really include that. But that's what it is. Now, this works much better than a simple threshold-based detector. Of course, it needs more complex processing, but I mean it's a filter. I mean these days, and on any even tiny microprocessor can handle these types of calculations. One thing that is a source of error for, so this is, for instance, it's unbiased. It's much less sensitive to the angle of arrival or the range of your target. It doesn't have all those drawbacks of simple threshold-based. But note that one thing that still is a source of error, even with the matched filtering, is that because of the physics of acoustic waves, your waves get distorted. The echoes that you receive back get distorted according to, for instance, the angle of arrival. So the waveform that you receive, in some cases, doesn't perfectly match what you transmitted. So there can be a little bit of distortion between the two, which degrades the quality of the correlation. If the two waveforms are not, perfect matches, your correlation can degrade. So your peak can be a little weaker. Nevertheless, this works beautifully. And as exactly was the case for GPS, the ideal, if you want to use this scheme of matched filtering, the ideal waveforms to transmit are going to be waveforms that have good correlation properties, right? So in the case of GPS, we saw M sequences were very desirable. It turns out that for sonar, M sequences are overkill. I mean, these sequences can be very long, and I mean they're good for very long distance ranging. Sonar, we just need to do a few meters. So there's some much simpler codes that exist that are used in sonar. Same principle. These are just waveforms with good autocorrelation properties. But for instance, Barker codes are type of ranging codes that are common in sonar. They operate, again, in the same way as M sequences. They're just shorter duration and more proper for short distance ranging. This should be very familiar, how you do your match filter ranging. Again, you receive your echo, you pass it through a correlator, you correlate it with your local replica of the waveform that you have transmitted, you get your correlation out, and then you square it, you take your absolute value, you find the peak, and the index corresponding to that peak, that is the discretized index for your tau, and then you do your tau hat, which is basically n hat tau times your sampling interval Ts. And then you convert tau hat to rho hat, which is your range, right? So that's how it works. And again, most common type of codes that are used, or waveforms that are used for this type of sonar, they're called Barker codes, which are signals with good correlation properties. Yes?
Why does your wideband waveforms also?
This down here, wideband waveforms. Well, it's actually, so maybe I should have written it the other way. So waveforms with good autocorrelation are desirable. We agree with that. They just turn out to be wideband. Signals that have good correlation properties, they always tend to be wideband signals. So that's why this is written that way. Questions? Yes?
Also affected by the angle. How is the performance affected by it?
Not as bad as the thresholding. So the question is this technique, is match filter ranging also, does it degrade with angle of arrival? A little bit, not as bad, like exponentially blowing up like the threshold based. And the reason it degrades a little bit is because there is some distortion in the waveforms that are angle dependent. So at steep angles of arrivals, the echo that you receive back, the waveform has some distortion in it, and that degrades the quality of the correlation. So essentially, like instead of, if you look at your absolute value of Rp times P hat, like for small angles of arrivals, it can give you like a very sharp peak, and then when your angle of arrival is larger, the peak can be a little, not as tall or not as sharp, but still, it's not like the error is going to blow up like the case of threshold-based ranging. So this is still a much, much better way of doing ranging. Okay, so this was for pulse echo sonar. Now we want to talk about the second category of waveforms, which were these continuous waveforms that are used for sonar ranging. So specifically, as we said, the waveforms that are used in CTFM sonar are frequency modulated. And there's a very, very interesting, clever type of frequency modulation that is used in these waveforms. And they are called linear frequency chirps. Okay? So what the signal waveform looks like that a CTFM system sends, let's call it S of t. And it has this very simple expression, e to the j 2 pi f0 plus b t over 2 times t. Okay, so let's break this down. So you have some start frequency f0 of your waveform, right? And then this b here is a constant called the slew rate. Okay, so what this is, let me clean this up a little bit, and let's call this term here everything. It's a phase term, right? So let's call that phi of t. So my S of t is equal to e to the j phi of t, right? Now let's find the instantaneous frequency of this signal S of t. By definition, the instantaneous frequency of a signal, let's call that f, is equal to the 1 over 2 pi times the derivative of its phase, right? That's a definition of the instantaneous frequency. So it's 1 over 2 pi d phi dt, right? So for instance, if phi of t, if my s was simply e to the j 2 pi f0 t, then according to this formula here, its instantaneous frequency would be just f0, which we know is true, right? This is slightly more complicated, but not too bad. We can take the derivative together of that phi. What it gives you after dividing by 2 pi, it gives you an f. So there's a 2 pi f0t. The derivative of that divided by 2 pi is just f0, and then you have a 2 pi times bt squared over 2, right? And then you take the derivative of that, and then that gives you a plus bt, right? So your frequency, you see, it starts at f0, and it linearly goes up or down according to what b is, positive or negative, over time. That's why it's called a linear frequency chirp. Graphically, they look like this. So a transmitted waveform. So this is for a positive B, what I've plotted here. So you start at some frequency, and as time goes by, you see the frequency is going up. It's you know, the oscillations are faster towards the end of the chirp compared to the beginning of it. And you do that for some time duration t, which is your big T, which is your chirp duration, and then you send another one. So you send a chirp, another chirp, and all of these are the exact same. But the point is you're continuously transmitting, right? There's no dead time. There's no stop time or silence time for your transmitter. Another way of visualizing this, which is perhaps more intuitive, is if you plot the instantaneous frequency of your signal as a function of time, it has this linear ramp, right? So at time 0, it starts at some f0 frequency, goes up with a slope of b, so you get to f0 plus b times t, where big T is a chirp duration, and then you repeat, right? Again, you drop back to f0, go up, and so on. So you send these sawtooth-like frequency chirps as a function of time. Okay? So how do we do ranging with this? Okay, so the echo that you receive is always just a time-delayed version of what you transmit, right? It also depends on angle of arrival and range, its amplitude. But here, we're focusing on that time of flight. So the P echo received, we can break it down into two terms. If S of t is that chirp waveform that we transmit, your received echo has some angle and range dependency times S of t minus tau, right? So if we look at the received echo and compare that to what we transmit. Let's look at this picture down here first, because I think that's very intuitive. So there's two things plotted here. The green is, again, that's instantaneous frequency versus time for what we transmit, right? It's just a ramp. And then the echo that you receive, that's also, I mean, it's the same waveform, it's just delayed, right? So some round trip time of flight has passed, some tau, and then you receive your echo. And the echo is the exact same, like in terms of instantaneous frequency, it's going to have the exact same behavior. It's a linear frequency chirp that is just delayed in time. That's the echo that you receive. So here, there's this very interesting relationship between your transmitted pulse and the echo that you receive, which is if you compare the instantaneous frequency of the two, it's going to be constant, right? This delta F here, as we call it, it's constant between the two, and it's equal to the slew rate B times the round trip time of flight tau. And we know tau is directly proportional to range, right? So we know the round trip delay is just 2 rho over V. So if you plug that in, you see that the difference in the instantaneous frequency of what you transmit and the echo that you receive is directly proportional to range, right? B is known. B is a slew rate that we choose and we use and we know. V is the speed of sound. And if we measure this delta F, which is the difference in the instantaneous frequency of the transmitted and received waves, then we can do ranging. So the beauty of this technique is that it kind of transforms a time estimation problem, a time of flight estimation problem, to a frequency estimation problem, right? Now by finding this frequency delta F, you can convert that to time, and you can convert time to distance, okay? And as you might know, frequency estimation, it's a problem that has been studied for many years in statistics and electrical engineering, so there are hundreds of different interesting techniques for frequency estimation, and all of those are now applicable to sensing, just by this little trick of designing a very interesting waveform. Is the concept of CTFM clear, how it operates? So now we just need to figure out how do we extract, so we have our transmitted waveform, we have a received waveform. How do we extract this delta F? If we can do it, just that piece, figure that out, then I think we are onto something. Yes?
Confused on the blind time, because isn't that usually like the periodicity of how long you're sending? Isn't T usually equal to the like 2 rho max over V?
Oh, I see what you're talking about. This T, right? Okay. Let me first talk briefly about blind time, because I didn't talk about it yet, and then I will get to your question. So there is always this blind time, and that's where a bit of time where your received echo, or the tail of it, basically, overlaps with the next chirp that you're sending. Okay, and this is a source of confusion, right? It's kind of like in the case of pulse echo, the question that had, which was like if your echo that you're receiving is after you have transmitted your next pulse, then you can't do ranging. So this portion is always ignored, okay? Or sometimes a bit of a dead time a bit of an idle time is added between transmitting 2 chirps, so this doesn't happen. But then question, you said, isn't T chosen to be 2 rho max over V? Well, that was the case for pulse echo, not for CTFM. So actually for CTFM, you want to choose your T to be much bigger than 2 rho max over V. So in comparison, this portion is actually negligible, and you can just throw out that part of the signal and only work with the piece where you know the signal is good. So that's the case. Okay. So in terms of the system block diagram of a CTFM sonar, this is it. Most of it is familiar, right? On the transmit side, again, you have your local oscillator, you have your waveform generator, which now generates these frequency chirps for you, right? It does this from F0 to F0 plus B times T. Continuously just does that. You amplify it. You might or might not have your transformer in the path. One big difference here is that because you're continuously transmitting in CTFM, you can't use the same transducer as transmitter and receiver because it will interfere with itself. It wouldn't know, like, what's the part that I was transmitting, what's the part I'm receiving. So usually you have a separate receiver transducer, and you have your separate transmitter. The transmitter is always transmitting, the receiver is always receiving. Receive signal, as usual, you pass it through an amplifier. Let's say it has some gain, constant gain mu. And the magic really happens here at this block here. This is the block that extracts that delta F for you, basically. And it's actually a very simple mathematical operation. It turns out that it's just a multiplication. It's also called a mixer or a down converter. So we'll see the exact math behind it, but then out of this, so you have to feed it 2 things, right? It needs to have your transmitted waveform or chirp, and it also needs your received echo, right? Because it needs to extract the difference in the instantaneous frequency of those 2. So if this is done right, then this is what we call S sub IF, IF for intermediate frequency. This should be a signal whose frequency is that delta F, which is proportional to the time of flight tau, if that's done right. And then you filter that, you take that through the ADC, and then you can do ranging and bearing estimation in the digital domain. Let's see. How much time do we have? Should we go through this? No, we're almost out of time. So we'll look at the math next time. But it's very simple. It's just a complex multiplication, and it extracts that delta F for you. But this is a good place to stop, and then we'll finish the discussion next time. Any questions? No. All right.